Good morning, good afternoon, or whenever you're watching this video. I want to bring you to the emergency department where there is a young boy. He's 18 years old and he was not feeling well lately. He lost weight, he had a foul smell and he's dyspneic. He's lying there and the emergency department doctor, he took an arterial blood gas, he takes it to you, he puts it under your nose and he says, well, would you be as kind as to analyze this blood gas? And that's what you're going to do, what we are going to do at this moment. You see it over here, this is what you see at that moment. This boy, he's got a pH of 7.15, where it should be around 7.40. His partial pressure of carbon dioxide is 12, normally around 40. Bicarbonate is 4 millimoles per liter, normal is 24. A negative base excess of minus 20.5 millimoles per liter should equal about 0, and the pressure of oxygen 128 millimeters of mercury. For those who are used to work with kilopascal, you should divide these two by 7.5. Okay, this is what you see. And we're trying to analyze this in 4 different steps, and in fact, all the blood gases can be analyzed in the same way in 4 steps. Let's start with step 1. I'll write it down here. It's for later. What's the first thing to do? The first thing to do is we watch the pH. What is it in fact, the pH? It's low. And what does it mean? It's the potentia hydrogeni. You might say that the power of the protons, because they're very powerful. In a more chemical way of saying, it's the minus logarithm of the proton concentration. Let's write that down on this side. It's a minus logarithm of the proton concentration. Normal, as we are sitting here and you're watching this video, I hope you're feeling well, it should equal 7.4. And for those who remember arithmetics on the high school, they know that this should equal 10 raised to the power of minus 7.4, which is the same as 40 nanomoles per liter. So the concentration of hydrogen atoms in your blood equals 40 nanomoles per liter. That's almost nothing. If you compare it to Berlin, let's say that every inhabitant is a sodium one, and there's only one in Berlin being a proton. They are very, very scarce. This is the beginning. So the concentration is very low, but they're very toxic. That's important to remember. And what do we call this pH of 7.15? Many people are used to say, well, call it acidosis. And strictly spoken, that is incorrect, because we are looking at the state of being, and we're not looking at the process. It means acidosis means the process which makes you acid. And we're looking at a state of being, namely 7.15. The more correct way of saying is acidemia. Acidemia. The blood is acid. Well, you can say, does that really matter? Well, it does matter because it can make a difference. Let's say that you've got a comparable boy, 18 years old, and he starts to vomit. By vomit, he loses acid, and his pH will raise from 7.4 maybe to, let's say, 7.8. At that moment, he's getting sicker and sicker. He gets hypovolemic shock. What will happen if people got hypovolemic shock? They start to metabolize glucose without oxygen. What does it deliver? It delivers lactic acid. They develop lactic acid acidosis. The pH was, however, 7.80 and will go down at this moment. And at a certain moment, it has to be 7.40. And it may be that exactly at this moment, I'm taking his blood for analysis. What do I find? I find complete normal values for blood gas. Does this boy have acidemia? No, he hasn't. His pH is 7.40. Does this boy have metabolic acidosis or acidosis? Yes, he has. Lactic acid acidosis. So in that case, it would be wrong to consider him having not metabolic acidosis. So it matters. That's point one. This boy has got an acidemia. And why does he have it? I use this for a second. That's the next step. So this boy has acidemia, so that means that he has to have acidosis. What is the cause of his acidosis? Then we go back to the basic equation. A proton plus bicarbonate dissociates in water and carbon dioxide. If there is a problem on this side, whether it goes up or goes down, we call it a respiratory disturbance. If there's a problem here, we call it metabolic. In the case of acidemia, will this be his problem? Then you would expect a high carbon dioxide, which is, as you can see, not the case. So it's not respiratory. Is it metabolic? Yes, because in acidemia you expect a low bicarbonate, and which is the case over here. So this boy has got a metabolic acidosis, which is in fact step 2, metabolic acidosis. There we go. Now we'll continue with step 3, and that's maybe the most tricky one, because step 3 is the question whether there is compensation or not. How does this boy compensate? He can do it by hyperventilation and losing carbon dioxide. Does he do it? Well, he does. It's lower than 40, so there is compensation. But then the tricky question, this compensation, is it adequate? Or in other words, is it complete? Or is it inadequate? And we call that partial. Many people think that because he is still acid, that his compensation is partial, but that is in fact not true. And why is it not true? Well, you already have a feeling, having a CO2 of 12, whoa, this boy is doing a great job. It's very low. And in a moral sense, in fact, you say to this boy, come on boy, you're hyperventilating well, but not well enough. Do a little bit more. Well, you can feel already that is nonsense. And physiologically spoken, the same, because imagine that you would be able to raise your pH to 7.40. But what, in fact, is the drive for breathing? That exactly is the pH. So if you would be able to normalize pH, then you lose your drive for breathing, and you would suddenly say, well, I'm there, I stop, I'm there, and you fall back to 12 breathings per minute or whatever. You get acid again, 40 frequency breathing, and you get up and down. Well, that doesn't sound very logical. So the question is, how do you consider this compensation partial or complete? There's another way. Don't consider the pH. There are two ways of considering this. The first one is a nomograph. For every bicarbonate below 24, minus 1 bicarbonate, your PCO2 should go down by about minus 1.3. So in this boy, his bicarbonate has decreased 20 millimoles per liter, so his PCO2 should decrease 1.3 times 20 is 26 millimeters mercury. It should be around 14. And what is it? It is 12. He is even doing better than this nomograph predicts. So this boy is doing a great job. This is what we call complete compensation. We can also have a sort of quick look, and it's an old trick. You don't find it so often in books, but it works. That you watch this PCO2 being 12, and you compare it to the pH behind the comma, which is 15. They resemble each other. If they do, then you say it's good. So that also means, because this resembles the pH behind the comma, there is complete compensation. This boy is doing his utmost best, and he's doing it very good. When you might say, do you call it incomplete or partial? Well, in fact, I don't know. I think if this should not be 12, but 18 or 19, well, never mind. Fair enough. If it's 22 for this young boy, well, it's not too good. I expected 14 or 12 and it's 20. And if it's 24 now, there we go. That's not good for this boy. We call it partial compensation, which means that this boy is in danger. A young vital boy should be able to compensate completely normally. And then he doesn't. In this case he does. So we call it step 3, complete compensation. We're going further on because we have only one step to go, and that step is considered by the PO2, the oxygen. Its rate is 128. How is that possible? Well, you might say this boy is hyperventilating. There is more air coming inside that raises PO2, but that is not true. Since bringing more air to you raises the volume of air and oxygen, but not the pressure. It might even go down, considering Bernoulli. If you shift air, pressure goes down. That's what a tornado does. So, in fact, it's not the inhalation, it's the exhalation that makes the difference. Because in your alveolus, there are 3 gases: nitrogen, carbon dioxide and oxygen. What does this boy? He's breathing his carbon dioxide out to the world, to the atmosphere, it disappears. So there will be room in this alveolus for pressure for oxygen. And in fact, when your lungs are functioning normally, your PO2 should be raised exactly to the same amount as your carbon dioxide is low. And you can see that this is exactly the case. So, point 4, this boy has what we call hyperoxemia, if it gets on the board. And then we reach the end of our journey, because I think we've got a complete analysis. This boy has got an acidemia caused by metabolic acidosis with a complete compensation with hyperoxemia. And that's it. And I thank you for watching this video.